All right. So my name's Emmanuel, and I work at the Java platform group at Oracle. I focus on the C2 compiler, which is HotSpot's most optimizing compiler, the JIT, as you might know. And most of my time currently goes towards working on auto-vectorization, but also reviewing and improving the vector API, hopefully making it ready. All right, so some of the things that I'll be talking about today, legal disclaimer, is not a promise. It's just things that we're developing, but we would love to hear your feedback. We'd love to have you try it out and tell us what works and what doesn't work yet so that we can make it better in the future. So it's an open source project, OpenJDK, so you're more than welcome to pitch in yourself. Okay, why vectorization? Well, it's really about parallel processing, and we've heard about parallel processing in all sorts of ways. Some of the talks have talked about Loom, about parallel threads and virtual threads. But really, we would like to get everything that we can even out of a single CPU, and that's where SIMD vectorization is really key. So our hardware gives us usually these wide vector registers that are somewhere in the vicinity of a cache line. Some hardware have shorter ones, some have longer ones, and they can hold multiple elements, let's say 4 integers, multiple shorts or bytes, and so on. So really, we'll only be talking about primitive data types just for now. So we have different element types and different vector lengths, as I've said. And the cool thing is if we have these vector instructions, we can really do multiple operations in a single instruction. That means we get more work done per cycle. We get more out of our CPU. And as I've said, there's different hardware implementations. So depending on what specific CPU you have different vector lengths or instructions that are available or not available. And so the JVM needs to kind of take that into account and figure out how to abstract over all that different hardware. Write once, run anywhere, right? That's the promise. And of course, vectorization can be applied in a lot of different fields. Classically, of course, linear algebra, but of course, AI, all sorts of simulations, physics, science simulations, or for fun, gaming, all sorts of processing, cryptography, financial time series, for example, or also a lot of the internals of the JDK have the ability to do things in parallel, for example, for arrays, strings, copying data, hash code, computation, and so on. So we want to really get the most out of our CPU that we can for all of these different applications. So today I'll be talking a bit about the auto-vectorizer, but then also about the vector API. They can complement each other in some ways, and I want to show you a bunch of different algorithms as examples. They are relatively simple so that you can see where to start, and then maybe you can figure out how to do more complicated cases. I have 2 demos as well, which are, medium complex examples that would show the application of those 2 techniques. So I'm thinking usually of 3 programming models that use vectorization, at least around the JDK. One would be the explicit, the automatic, and the intrinsic. So explicit means really what we want to do is we want to use assembly instructions, vectorized assembly instructions, as directly as we can. And Java's vector API allows us to do that and have this almost one-to-one connection to these juicy CPU capabilities. So the cool thing is if you use something like the vector API, you're already writing your algorithm in vectors, and then the one-to-one translation to assembly instructions that are vectorized is a bit more guaranteed than other techniques. But of course, for you as a Java developer, this requires more time to think about your algorithms in terms of vectorized instructions rather than just single elements or whole data structures. If you're not really worried about performance, you can still rely on the auto-vectorizer. In many cases, it will do the job for you. You just write your regular Java code, single element fashion, and you hope that automatically the compiler optimizes it for you and uses vector instructions. This can be great overall for all sorts of different software, for all sorts of different cases, but for your specific case, there's not really a guarantee that it's going to kick in and going to optimize your case. You might make small changes to the source code in Java, and then it might mean that either the pattern is now recognized or not recognized, and this can lead to some brittleness. We're working on that. We're extending the pattern matching capability of the optimizations, but it will always be limited. And then there are some core library methods in Java that are so important and pretty clearly parallelizable. that we have for a long time already been handwriting assembly for those Java calls, essentially. So instead of filling the fill call, instead of going to the Java implementation and then compiling that, we actually directly call an assembly snippet that has been handcrafted. And of course, we need to do that for each CPU type, so there's a bit of overhead to do that for us as JDK developers. But it's very important for arrays, strings, and crypto computations that really we would like to get the optimal performance. And as I've said, it takes a lot for us to do that, though. Okay, so let's dive a little bit for a quick second into auto-vectorizing. The algorithm here that we have in C2, that's HotSpot JIT, is SuperWord, and this algorithm exists already for a long time and has been implemented for a long time in the C2 JIT. Its basic idea of this paper was to find sort of parallel statements. They are isomorphic, so they all have the same form, and so we can pack across those instructions into vectors and then use SIMD operations, which should hopefully execute our code faster. In C2, we take loops and unroll them. So that means maybe 4 times unrolling or 64 times unrolling, depends on what we do specifically. And then we have to restructure this unrolled code. That's what the SuperWord algorithm does, and it packs it into vectors, right? It means reordering instructions and proving that that's okay. And as I've said, we've done that for a long time, and over time we've just improved the pattern matching capabilities, added more instructions that are vectorized, and so on. And even in JDK 26, which was just released last week, we've made more improvements to the auto-vectorizer. All right, I'll venture to give you a quick demo. So this demo here is maybe something you'd actually run on a GPU, but your CPU will be already pretty good at running this. So it's the idea is that you have in 3D visualization, you often have a lot of triangles, right? And you want to reduce the number of triangles. And so what you do is you create this normal map that sort of represents the local structure in your flat surface. And you can represent it as an RGB color, which actually is an XYZ normal direction. And then with a little bit of vector math, you can take the direction of the light and of this normal angle and compute if the specific pixel is going to be bright and how bright, or if it's going to be shadow. And so here I wrote this up one afternoon. It's basically a big loop that goes over all the pixels on the screen and then executes this snippet of Java code for each of those pixels. And what you can see in this code, if you investigate a little bit, it's of course independent for each of the pixels, for each of the iterations. And so it's a good candidate for auto-vectorization. All right, so let me run the normal mapping demo first. Yes, so you can see that I disable SuperWord with the -use SuperWord at first. So that's just to show performance that we have without the auto-vectorizer. On the right side, you see sort of the normal map, and on the left, you should see how the lights illuminate the surface. And we are now at about 36 FPS, and after a while, it cycles through to other visualizations. So now let's see how fast we get if we enable SuperWord, which is of course enabled by default. So I just removed this sort of testing flag here. And now we see the FPS soar up to, maybe 130 FPS. That's on my laptop. It might be different on your laptop or on your server machine, but it's just to show that you can get significant speed up if you have a loop that the auto-vectorizer succeeds. All right, back to the presentation. Good. Now let's look at the vector API. So in some cases, the auto-vectorizer is not going to kick in, as I've said, because maybe it doesn't pattern match your case. And you might want to have more guarantees that your code is optimized and uses those juicy vector instructions. And so we want you to be able to express your vector computations directly in Java and not have to resort to CPU instructions on your specific machine. So in Java code, usually classically you would use individual arrays that you're accessing, loading, adding, and storing. But with the vector API, you can load whole vectors of data and add them, let's say element-wise, and store them back somewhere. And that's kind of a little snippet that would show that. So I call the single element sort of operations scalar, and the ones that use multiple elements vector. That comes from Mathland, I suppose. So as I've said, it's all about expressing vector computations directly in Java so that you can have a bit of a guarantee to go directly down to the CPU's vector instructions and really make the best use of your CPU. And it's especially helpful if the auto-vectorizer doesn't yet match your pattern. So the goal is to give you this really sweet, nice, and concise API that's portable, like Java is portable. So write it once, run it anywhere, at least in theory. That's the goal. But of course, here it's all about performance. It's not just about generally running it anywhere, but it's getting as most as we can out of the machine. So whenever the instructions are available on your CPU, we should be trying to use it. That's the goal. But of course, not every CPU implements all of those instructions that we have in the API. And so then we need to fall back to some sort of simulation of the vector instructions. And so we should try to be at least as fast as single element algorithms would be. It would be a shame if you first wrote your single element scalar implementation, then took the hours it takes to write your vector API implementation, and then that one would be slower on some platforms. Like that would be sad, right? So we try to figure out a way to make it at least as fast. That's a goal that we so far haven't addressed, and I hope we can work on that in the next year or so. So of course, the Vector API hasn't yet been released. It's been in incubator, and it's been in incubator for a long time, for 11 releases so far. And the reason for that is that we're waiting for Valhalla. We've been waiting for Valhalla for a long time, but I really have some confidence that it's coming soonish. And of course, then after some releases, we want to then also put the Vector API into preview, which means it should be more generally available. All right, so back to the API. The API can load and store whole vectors, and you can say how many bits the vector should have. So here, 128 bits would be for integers. You load those, and you store those back somewhere else. Then we have lane-wise operations that take two vectors and element-wise or lane-wise add them up. Or you do multiplications, or there's a whole long catalog. I only have a few of them here on the screen of operations that you can choose from. And then there is much more. So there are masked operations. We'll see a bunch of examples for that. So it's about making comparisons and enabling, disabling lanes and blending together results. So for example, you might load a vector of data, then compare which values are larger or equal to 0. You get a true or a false per lane, and then you can use that to do some sort of masked operation like a masked store that only stores those entries that have a true value and the other values stay untouched. You can rearrange, shift around data. So for example, you might have a shuffle vector that has reverse indices. This allows you to revert a whole vector in a single instruction. Hopefully this would allow you then to reverse a whole array of data. And then we can do things like casting, reinterpreting, and so on. So we might want to cast integers to longs, and that might change the size of our elements and also of the vector itself. All right, now that we have some basics covered, I want to go through some vectorized algorithms, and they're going to be relatively simple, just simple loops of some pretty primitive things we might want to do, might remind you of some things that we do with streams. And so we want to see how the Vector API and auto-vectorizer can be used here and how far we can go with it. So the first thing would be just fill an array, pretty simple. For that, we have arrays.fill, which is from the core libraries, and it actually is backed by a vectorized intrinsic. So there is this snippet of assembly that backs it. And so I would recommend that you try that first. Just use that and don't hand roll your own code. But of course, you can hand roll your own code, and then this should get auto-vectorized or replaced with an intrinsic in this case, actually. But since this code shape is so simple, it should get optimized. Then you can also use the Vector API and manually vectorize here. So what you would do is you would fill a vector with each element number 42. And then you would stamp down a whole vector's worth of data and increment by the vector length. So maybe by 4 elements each time. But we have to be a little bit careful with the loop bounds here. We might overshoot the array, so let's not do that. So in the first instance, we might fill with 4 elements and another 4, and then we have to figure out how to fill the individual remaining elements at the end and currently the most performance solution is to write 2 loops, one vectorized that fills up as much as it can with the vectorized code, and then a scalar loop. We know this is inconvenient. It's currently the fastest we can do. Maybe we can eventually figure out a way that you can only write 1 loop with masks, but sadly masks are slow for now. So I have an idea for the optimization, but we haven't implemented as of yet. All right, let's go to mapping. So mapping, we take a value, do some operation with it, and store it back. Here, multiply with 42. This should also get auto-vectorized. It depends a little bit on what's the mapping operation, but most operations should be okay. But, please profile it yourself. We've had a lot of talks about profiling, so it's important that you really measure what you get and don't just speculate. I have had a lot of interactions with people that speculate to say, oh, maybe this should work, why doesn't it work? And they're frustrated. Well, go and benchmark, and then if something doesn't work, please contact us, because we would like to know which cases that you care about, and we can maybe improve for the future. All right, okay. In this case also we can use the vector API to do it. What we'll do is we'll load values and then element-wise multiply all of those with 42, and here the number 42 is automatically broadcast so that it is an element-wise multiplication. Reductions. So reductions are about taking a whole container of elements, an array for example, and crunching it down to a single value. This might be a sum, this might be a dot product, which takes actually 2 arrays, or finding the maximum, minimum. There's plenty of operators like that form reductions. The performance bottleneck here is most likely going to be the latency at first. So if we run this in scalar code, the problem is that when you go through the summation, that each addition instruction needs to compute its result before the next one can be scheduled. And so if you have this nice super hyperscaling CPU that could actually execute things in parallel, you're still going to wait for all of the cycles for an addition to complete, and then the next one to go to be scheduled, and so on. So the latency of our whole reduction chain is the problem at first, and we need to figure out a way to crunch this latency down, reorder instructions somehow to make it work. So if you use the vector API, and actually auto-vectorization uses similar tricks, where we have this reduce lanes operator. What it does, it takes a vector of values and recursively cuts it in half and adds it element-wise until we end up with a single element. I call this recursive folding. And now the cool thing is that along the reduction chain, we now only have, in this case, a fourth as many numbers to add up. So our latency has been cut down by a factor of 4. So that should be a big win. However, there is now another issue, which is that such a reduce lanes operation is now executed in each vectorized loop iteration. And it actually requires a lot of assembly instructions in the backend to execute those. So now we're jamming a lot of those instructions through the CPU, and we end up being quite throughput bound on the CPU. So we would like to find a way to now use fewer instructions per vectorized loop iteration. So what could we do here? Well, we just moved this reduce lanes operation outside the loop. And instead of using a scalar single element sum, we use this vectorized accumulator. So we fill it at the beginning with all zeros. And then we add in element-wise all of our new values, right? And we keep on doing that. And what you see is that this vector has all of the different elements, and an individual element holds a part of the sum. And if we crunch together the whole vector, we get the total sum. So if we do the reduction at the end of the vector, then we get the total sum up to now. So what you see now is actually we only have a single element-wise operation per vectorized loop iteration. So we actually have a fourth as many instructions as we did at the very beginning, and the latency has also been cut down by roughly a number of 4. So at least in theory, this should give us a solid speed up. Okay, so I'm not going to talk about this in detail, but basically over the different JDK versions, starting at JDK 9, we started to also in the auto-vectorizer use these kinds of techniques to speed up different reduction patterns. If you want to know about the details, you can go look at my blog. I'll bring it up a few times, and at the end, the URL as well. And even at JDK 26, we've now improved some things about reductions. So we're on that. So this was though only really about sort of integer values. And as soon as we go to look at floats and doubles, which are very important for scientific computations and simulations and so on, and also for AI, we often have floating kinds of numbers that we want to compute, something like a dot product. And the problem is, if we hand roll this in Java, then we use single element in operations, right? But now we would like to use this recursive folding technique to get the speed up or the vector accumulator, but all of that requires us to reorder the summation. And the problem is, if you do that, then you might get different rounding results. And that's just not allowed from the Java spec. So we can't optimize that for you, but you are allowed to, of course, use the vector API, and the reduce lanes operation is allowed, actively allowed to do this reordering. And so it might produce slightly different rounding errors. You need to be aware of that. If that's okay for you, then you can use it and get according speedups. So let's say for dot product, at the very end there, we actually have only an element-wise multiplication and addition inside the loop. So that's really performant. And we can even collapse that to an FMA instruction, fused multiply add instruction to, on some platforms, get even a slight edge on top of what I have here on the screen. Now, real-world applications, for example, Netflix, earlier this month has used the vector API using the dot product for their ranker system. There was this blog post, and basically what they do is they take both videos and user histories, and they use a vector embedding to get sort of arrays of data, I suppose. And then if they're close in the vector space, that means they're similar. So you have similar histories or similar videos, that helps you make recommendations. And to compute this similarity, we use the dot product, and they have this code there, and that's pretty much what I had on the last slides. They're using the FMA instruction as well, and they get significant speedups, of course. Computing the dot product is not all their workload does, so they only get a speed up on part of their software, but even that is in the range of 7 to 10 to 12% depending on the metric. So that's significant if you're running a Netflix scale. Back to the vectorized algorithms, copy. You might think that's trivial, but there's some catches there as well, at least in the details. You should probably be using system.array copy if you can, because it's, again, backed by a vectorized intrinsic. But if you want to, you roll your own code, and it should get auto-vectorized. Maybe some issues with brittleness here, and we've been working on that. Talk about that in a minute. If you use the vector API, it's just a load and a store. However, be careful here with overlap. So most of the time, the region that we load from and store to, there is not an overlap. So imagine we have like this rainbow of input values that we get, and then we copy it. And we can do that basically either by copying the whole rainbow and just plopping it in, sort of in parallel or in bulk. But of course, the semantics behind the scenes is element by element, and we need to make sure that that's the same that we do. But in this case, where there's no overlap, it is the same. No interference between loads and stores, and it's basically clearly parallel, so we can use vectorization, which is a form of parallelization. Though if we have overlap, then we need to be very careful, because we can't just bulk copy this rainbow of values. Instead, we do it element by element. We see that we actually overwrite some of our values that we should then be copying from. And so instead of finishing the second half of the rainbow, we actually take the first half of the rainbow and fill those values in. So now we need to be very careful, because the parallelized and the scalar implementation do something different. And of course, a compiler cannot optimize and then behave differently. That's not okay. So we couldn't just optimize this. And so the compiler, in many cases, it will know that it's not overlapping, but in some cases, it cannot prove it. And especially with things like the memory segment, which is part of the project Panama, to also interact in a better way with foreign memory. There we have the problem that we basically never know if it's overlapping or not. And so we've really had to invest a bit of time to make that happen, so that we can vectorize in cases where we at runtime can prove that we have no overlap. And so that's what we've added in JDK 26. Basically just a runtime check that checks is there overlap or not. If it doesn't overlap, we can use the fast vectorized code. And if it does overlap, then we use some slower code to back it up and be safe. Okay, so that's the performance difference on one of the benchmarks that I have. So in JDK 25, we see the performance is a bit slower, takes more time to compute. In JDK 26, it's a bit faster. I did a lot of repetitions so that you see there is a little bit of jitter there. We might want to talk about that in a second, why there is some jitter. But the clear difference is from scalar to vector. That's a huge win. Then I used the vector API as an implementation that also works with arrays. And we see it's pretty similar to the auto-vectorized code, but it's sometimes slower. Sometimes it's the same speed. And it seems to be like multimodal. There's like these funny different lines. Sometimes it's very fast. Sometimes it's a little bit slower. Sometimes even yet a little bit slower. And the problem here is alignment. I ran this on an AVX machine, and here alignment, you can be misaligned, but then you're a little bit slower. So I'm not going to talk more about this in detail, but please read the blog post if this is important to you. If you do some sort of micro benchmarking using the vector API, you might get multimodal performance, and it's important for you to know about that if you do those micro benchmarks. If you want to get really the last edge of aligned performance, you can use the vector API with native memory using the FFM API and make sure that the memory is aligned. Then you have full control and get maximum performance. All right, now let's shift gears and go to some loops that use control flow. Here, lowercasing a string. Well, here's just a byte array. I load the bytes. I check, is it in the ASCII bound of uppercase characters? If it is, then I transform them to lowercase characters, which happen to be an addition of 32. Then they're in the lowercase bound. So again, this is my hand-rolled loop here. It's not auto-vectorized, sadly, because it has control flow. C2 doesn't handle that yet for the auto-vectorizer. Might do it in the future, hopefully. So if we get a lowercase character, we do nothing and just store the value. If we get an uppercase character, we have to do the addition. So you get kind of the diamond shape and the control flow here. We can use the vector API with these compare and mask instructions. So you would load a value, then do the comparison for the upper bound and the lower bound for all of the elements, then do an AND to get where we have true in both cases, and then use a masked operation for addition. So only where the mask is true, we do the number 32 addition, and in the other cases, we do nothing or add 0. Then we can store those values back. Now let's look at the performance numbers for this. So I have both the vector API and the scalar solution here, and we see that it has a clear performance difference, a big win of maybe factor of 16 at least. But it depends a little bit on the input, how big the speedup is. So if I mostly throw lowercase characters in our input string, then that's one behavior. If it's mixed 50-50, that's one behavior. And if it's mostly uppercase characters, that's yet another behavior. So for the scalar implementation, if we have mostly lowercase character, the branch predictor will go down of doing the nothing branch, right? And it's going to be relatively fast. If it's mostly uppercase character, it's going to go predict mostly the adding to the lower casing branch, right? But it's in the middle, then the branch is very unpredictable. And if we have an unpredictable branch, we get a lot of branch mispredictions, and we have a lot of misprediction penalties. On an ARM Neon machine, on a different machine, the performance speedup is maybe factor 10, 12 at least. And we also see the same branch misprediction penalty. In this benchmark, the performance is, the patterns are very comparable. But what's the lesson here is that if you have some branching behavior, you need to be very careful about the input data, because the speedups that you might measure are going to be different if you give it different kinds of inputs. All right, now a second sort of example is this piecewise function. So what I want to do is for each input, I want to apply this piecewise function. So I feed in an x, and if the x is smaller than 1, I do multiplications, and if it's larger than 1, I do square roots. You have to know that computing square roots is quite expensive compared to multiplications. Now, for the vector API, what I can do is I can do a comparison, right? But then I have to compute the results for both the multiplication branch and the square root branch for all of the elements, and then I just blend together the values, whichever one I had to take, given the mask. If I now look at the performance on my x86 machine, I see that if I feed in mostly values that lead to square roots, the scalar performance is quite slow. It does all those square root computations, which is slow. And then if I go mostly multiplications, then it's quite fast. There's a transition point in the middle, and the vector API solution has steady performance because those masking comparing operations are actually executed unconditionally. They're always executed, so there's no dependence on the branching probability there. Now, if I go to another machine, the performance numbers might look different. So again, please benchmark your results. They might be different on different machines, and it's significant. It's also significant which solution might win out because we're getting pretty close to the hardware here. So maybe what could we do to improve the vector API solution here? We'd like to get better with the mostly multiplications. And the problem is that currently we're even doing square roots if we should be only doing multiplications. And so we can combine vectorization and branching. With this solution here, basically I do a check. Is any mask bit such that I need a square root, and only if one of them at least needs the square root, then I compute it. And this way I can then get rid of the extra cost of computing the square roots, and I can get better on that side. So I know this is pretty detailed, but I think it might be important for some of your workloads to be aware of the cost of branching, branch misprediction, and the implication when you vectorize. All right, yet another case is filtering. So here what we do is, again, handwritten loop. C2 doesn't optimize it because of the control flow. And what we want to do is we want to keep the numbers that are larger or equal to 0, right? And kind of copy and compact them to a new array. So if a value gives us false, we just do nothing with it. And if it's true, we store it into the next available position and increment our counter. The trouble here is with the counter that it only increments when the bit is true, right? And so it kind of depends on how many previous iterations were true, where our new element is going, and that at first is not clear how we can parallelize that. But the vector API has a way of doing that, at least on the vector side, so we can compress on a vector of data. So we might get a vector of 4 elements, then check, okay, 2 of them are larger or equal to 0. Then we compress both the input values to the front, but also the mask bits to the front, which allows us now to do a masked store operation where all of the values are compressed to the front. And we only store those and only touch memory where we need to. Then we also increment the counter by however many elements were true, so that we can then in the next iteration plop in the next values, right? And so sometimes we store no values, sometimes we store the whole vector, sometimes a part of it. But the cool thing is that we can do multiple input values at a time. That's where we get the speed up. I'm not saying this is the fastest possible implementation, but that's, one that's, I think, instructive. All right, so the performance here on an x86 machine, again, the scalar is slower than the vector API solution. We see that filter has a branch, so we see the classic branch misprediction peak in the middle. The vector API implementation uses compress, that's executed unconditionally. And so that's great. The vector API wins again. And we see that if we reject values, we do nothing using the scalar implementation, right? And if we mostly take values, then we do the store. So that takes a little bit more time on the scalar solution. There's a bit of a caveat for now. The vector API has some cases where if the instructions aren't available on your chip, then we fall back to some really quite slow Java code that does a lot of array allocations at each step. And so the problem is now the performance is orders of magnitude slower. And so we haven't really fully achieved yet the graceful degradation at this point. And that's something that we are considering to work on soon, hopefully. So in practical terms, you could use the vector API as it is, and it may always be that you have to benchmark and compare your scalar and vector implementation and see what the input values are. And then for each architecture, you might have to make the decision which one is faster for your use case. All right, so now a quick demo using the vector API. I love writing little simulations, and I found this on YouTube where someone had this particle life simulation with particles. It's essentially an n-body simulation, so kind of a physics-inspired simulation where each particle interacts with each other particle depending on the distance. They have different forces and also different colors like or dislike each other. So we have this function that gets applied for the distance. And so if 2 particles are very close, they repel each other. And if they're in a medium distance, they either attract or repel each other depending on the pairs of colors, right? If they like or dislike each other. Okay, so I write a scalar implementation here with a double loop, each particle against each other particle, and then I compute the distance as well as the force. And the force here is this piecewise linear function. So I have these if-else blocks here. I'm not saying this is the best scalar code, but that's what I wrote this afternoon. And so now if we vectorize this, what we could do, for example, is one solution is having one particle in the outer loop and a vector of particles in the inner loop. And then, of course, we do the distance computation and the force computation using these vectorized instructions. And instead of control flow for the force computation, we use compare and mask and blend instructions to simulate this control flow. All right, now let's go look at the simulation for that. Okay, so for now, you still have to add the module, right? Because it's only in incubator mode. So you have to kind of tell the VM to allow to run this. And if I do, I see some particles that are floating around. I have here some knobs to change the simulation, right? I can adjust it a little bit. And what we see is it's stabilizing at 23 FPS using the scalar implementation here. And then if I swap out to this first vector API implementation, it takes a second or so to spin up, compile the code because I haven't touched it before, right? The compiler hasn't seen it before, so now it's compiling. Now it's running at about 130 FPS. It looks pretty wild. And then I had a colleague of mine review the code, and he was like, "Ooh, you could even optimize the vector instructions a little bit here, reorder some things." And he had another idea how to improve it, and now we're at like 107, 180 FPS. So yeah, as I said, I love like little physics simulations, or maybe you were writing a game or something like that. And I hope that the Vector API could be useful for computing things faster. And all of it is in Java. So, you don't have to go out to native code and use some sort of C compiler and unsafe code, but you stay within the guarantees of Java, which is hopefully good for you. All right, so that's my summary slide. We've seen intrinsics, especially important for core library methods. So if you can use core library methods because they might be optimized more than alternatives, auto-vectorization would give you free speed up. If you don't super care about performance, it's there for you. But it can be a little bit brittle because if you change your source code just ever so slightly, it might kick you out of what the auto-vectorizer can currently recognize. And JDK26 was released last week, and some changes made it into there. For example, again, this aliasing overlap check, and also reductions were improved, but also plenty of other things. The Vector API should give you cross-platform access to these juicy vector instructions. So that means a bit more guarantee on the performance side. And it's especially useful if auto-vectorization doesn't work out for you. But again, it's at this point only in incubator mode. Some people are already using it in production, but you have to know yourself if that's okay for you, or if you need to wait for preview or the general release later on. If you want to know more details, I've written some blog articles on a lot of these topics, and I have more examples there, some benchmarks you might want to play with. But again, we have heard it in some other talks. If you're using the Vector API, and if you're thinking, oh, maybe this should vectorize or not, don't guess. Please go and measure, write a benchmark to be sure that it works in your case. Right. And then there's some things that you should definitely learn if you're using vector instructions and performance benchmarking at this low level, at this very specific sliver. Then you should know about branch prediction, latency and throughput of instructions that go through your CPU pipeline, as well as memory alignment of the vectorized loads and stores. It has an impact on some platforms, but not on others. Then if you're using floats and doubles to do, let's say, summation and dot products, then be aware that the Java auto-vectorizer isn't allowed to optimize it because of the rounding issues, so maybe the Vector API would eventually be the solution for you there. And last but not least, OpenJDK is open to the community. A lot of people contribute to it, various companies, and also hobbyists. We've seen a lot, and we reviewed our code, and some of them are really amazing. So a shout out to them. Something that I would love to see, and actually one or two people already talked to me about that and have some things that I might be able to look at later. I would love to see more demos that prove out the Vector API, see the weaknesses in it, see more vectorized algorithms that go a bit beyond the complexity that I show you today, just to maybe even write something that could be useful for other people, that are algorithms that people might use. So that'd be amazing to see. And of course, I always love to see real life applications like the one we saw from Netflix, but there's some others as well. So if you have some of those, please let them come our way. All right. I hope this was interesting to you. I'd love to hear your questions or talk to you later if you're still around. No, there isn't. I think in the end, if you want to know does it work or not, you have to look at the assembly, right? Oops, sorry. You look at the assembly. Did it work or not? That's, I think, the most straightforward thing to do. You might be able to do that through a profiler. The thing with emitting warnings, it's a bit tricky because there are, in the whole optimization pipeline, right? It's like a whole bunch of different optimizations. And so the thing is, if you have a loop, how are we supposed to know that you expect it to vectorize? Some loops are like, you never expect them to vectorize. So how are we going to tell that, right? And so it might be that, for example, the problem isn't actually with the auto-vectorizer, but maybe with range check elimination. If the range checks haven't been eliminated, we can't auto-vectorize it. And so maybe you have some sort of addressing pattern that's just too complicated for us to recognize. Then we fail at that early stage. So it's actually a little tricky to give you the answer there. But if you have an idea, then let me know. It's a problem I'd love to solve and give better feedback. Mm-hmm.
So, do you like compare your algorithms to, I don't know, GCC, C-lang, like compilers from? Because I was actually surprised that they were pretty good like a few years ago.
You mean like more the C++ compilers? Yeah. I mean, I'd love to, but I think in the recent years there hasn't been as much investment into the auto-vectorizer. Maybe also with the reason that Java uses a lot more objects, and with objects it's harder to auto-vectorize, right? So we're not really quite at that low-level point. For example, if you look at streams, right, they wrap everything in objects, and auto-vectorization at this point is far away from working for that.
Surprised that when I write the code with vectors on my own, he actually produced better code than I.
Oh yeah. Like
assembly.
Yeah. Right, exactly. Like even if you have the vector API, you're not gonna get yet perfect performance. You might have to tweak it a bit because like the auto-vectorizers that are really amazing, they know a lot about how to unroll your code and so on. So it is still an art, right? But you will get significant speed ups for even using it, and then the capability to do it within Java. That's the main promise there, I think.
Hello, thanks for your presentation. I would like to ask you about the streams now that you mentioned it. What about there? Is there some auto-vectorization there when we do for each, for example?
Yes, so I've seen some examples, but they are the really basic ones where you don't have objects. So you really need to avoid objects. But if you have an int stream for each, there are some cases that do get auto-vectorized. I've seen those before. Yes, but again, you have to look at the assembly. But yeah, it would be lovely to do more there. I have some ideas how to even auto-vectorize with objects, but then you get into trouble with the GC and so on. So it gets tricky. Yeah.
Thanks.
Thanks for the questions.